Hi, good morning to all. So let's continue from where we left yesterday. So yesterday we essentially talked about the historical development of the standard model, and we saw how our tools kept on developing, starting right from cathode ray tube now to, of course, the most modern apparatus like the Atlas or the CMS detectors. If you were observant, I have changed my plan slightly. So today I talk about not yet. Okay, is that better? Okay, yeah. So today I talk about theoretical foundations of the standard model, but I will restrict myself talking only about gauge symmetries and electrochemic symmetry breaking, which form two of the major pillars on which we build the standard model. And I will spend tomorrow's lecture talking about the flavor structure of the standard model. So today I will not spend much time on flavor, but tomorrow in its full glory, we will try to look at the flavor part of the standard model. Okay. So we all know this, we have seen this many times. We can count number of particles. I think here, if you count it like this, they'll come out to be 17. But all of us know that this count is not correct. Right? So first reason is because the quarks that six quarks that we see here, all come in three colors. Okay, so which means that if I really want to write everything, I should write U quark 3 times, C quark 3 times, and T quark 3 times. So all the quarks I should write 3 times, UD, CS, and TB. More than that, I also know that each particle has its own antiparticle. Okay, and therefore, for each up type quark, I will have a down type quark. Sorry, for each up type quark, I'll have an anti-up quark or up anti-quark. For every strange quark, I'll have a strange anti-quark, and so on and so forth. So everything will have a partner which is own antiparticle. Neutrinos have antineutrinos, electrons have positrons, muons have antimuons, and so on. Gluons, there are of course 8 of them, okay, and not just one, as we saw in the last slide. So we will have these 8 gluons, and we will talk about why they are 8, where does 8 come from in a short while. These are our W plus, W minus, and Z. This is photon, and this is the Higgs boson. Okay, so if I may say so, this is the extended version when I write all particles separately. Actually, I haven't completed yet, okay? Because this is still not everything, because most of these particles actually come in 2 varieties, right-handed and left-handed. Okay? And in fact, as you know, they have different properties. Standard model is so-called chiral theory, which means left-handed particles and right-handed particles have different properties, and therefore it is important to also count them separately. So what is this chiral property? So of course, we do standard model as a quantum field theory, which is based on basically relativistic quantum mechanics, in which you write each fermion as a Dirac spinner, which looks like this, psi, and then you have its left chiral component, which you obtain by multiplying this spinner by 1 minus gamma phi upon 2, and you call this as the left chiral component. Whereas if you multiply this by the matrix 1 plus gamma phi by 2, you will call that a right chiral component. And these are our left-handed and right-handed quarks, or right-handed and left-handed leptons, whichever particles we are talking about. Okay, so it's important to think of, when you think of standard model particles, not think of an electron, but think of a left chiral electron and right chiral electron, because they are going to have different properties, as we will see very, very soon. We know it already, right? A left chiral electron will interact with W boson. A right chiral electron will not interact with W boson. Okay, so it's not just the fact that they have different chiralities, but their interactions also differ. Okay? And the fact that they differ is actually a very important part of the theoretical structure of standard model. Okay? So I wanted to emphasize. So all fermions in the standard model, except neutrinos, have both of these left and right chiral varieties, like EL and ER for electrons. But for neutrinos, we know there is a left chiral neutrino. We don't know if there's a right chiral neutrino. The fact that neutrinos have masses maybe leads us to suspect that there could be a right chiral neutrino. But as we talked about this many times yesterday, just thinking that something explains something is not discovery. We have not seen the right chiral neutrino yet. I also want to emphasize here, although I won't go into detail, is that chirality is not the same as helicity. So I usually try to be very, very careful in talking about left-handed or right-handed particles. That's the common terminology used. But left-handed is sometimes used for left helicity or right helicity particles. Helicity and chirality are different. We will, when we talk about standard model, when I say left-handed, when I'm not careful, I am always talking about left chiral, okay? Because chirality is a relativistically well-defined quantity, and therefore, when we talk about EL and ER, I'll be talking about left chiral electron and right chiral electron. So, okay. So in addition to all the particles that we saw on the last slide, most of them are actually doubled, except for neutrinos, by having a left and right chiral components. Okay. So this was listing of particles, but listing of particles is not standard model. Okay. So standard model also describes interactions among the particles in a theoretically consistent way. Okay. And in fact, that is the main thing about standard model. It is not a dictionary of particles and how they interact. It is the discovery of a pattern in the interactions within these particles, among these particles. Okay. So of course, no, there are 4 interactions. Standard model does not concern itself with gravity. We do not know how to do this yet, but we will be combining electromagnetic, strong, and weak forces together through symmetries that we call as gauge symmetries. So most of the time of today, we'll actually go in trying to describe what the gauge symmetries are in a way that I don't know how many of you have studied gauge symmetries. Maybe I can have a raise of hands. And that will tell me, okay, good. So half, more than half. Okay, good. Yeah, so thanks. Okay, so before you go to gauge symmetries, okay, let me just remind you of the Euler-Lagrange equation of motion in classical mechanics. So in classical mechanics, what do you have? You have a Lagrangian, okay, L, and then if you have a variable Q, which is the generalized coordinate, then you get this Euler-Lagrange equation, which is d by dt of del L by del V or del Q dot, if you like Goldstein, minus del L by del Q equal to 0, and that's your Euler-Lagrange equation. Exactly very similar equation also appears in the case of quantum field theory language. Only thing is how here you talk in terms of Lagrangian density, okay, in the 4-dimensional space, and now your corresponding equation to the Euler-Lagrange equation becomes something like this. So instead of del L by del V, we have del L by derivative of phi, okay, with respect to any of the 4 variables, 4 space-time variables, x, y, z, t. You take this derivative, you instead of doing d by dt, you do del by del x mu, with the same variable here, minus del A by del phi is equal to 0. Okay. So when we do quantum field theory, a very simple rule of thumb is you look at a Lagrangian and try to write down this equation. That equation will tell you how a certain field is going to be. Okay. It's of course good to know where this comes from, but we will not go into that at the moment. Okay. In standard model, we have mostly spin-half fermions. So how do they behave? Okay. So Lagrangian, of course, tells us exactly how they will behave. If you have a free fermion, then the Lagrangian will be psi bar I gamma mu del mu minus m times psi. Gamma mu's are, of course, the Dirac matrices. I hope all of you are familiar with this. And psi is the spinner that we saw some time back. Okay. So if you try to form the Euler-Lagrange equation from this, you get two equations. One is I times gamma mu del mu minus m times psi is 0, and other is its Hermitian conjugate. Okay? And these equations tell you how psi behaves, right? So if psi is an electron, this equation is going to tell you how an electron will behave, okay? How the derivative of electron field wave function will depend on the mass of the electron, and so on. Okay, so that is the rough idea of how we are going to start. So let's go to electromagnetic interactions, try to understand them in the language of gauge theories. Yesterday we saw that Feynman and company, when they developed electro theory of quantum electrodynamics, essentially said that the force between two electrons is because of exchange of photons. Right? So that was one way of looking at it. Okay, let's try to look at it in a more theoretical way. What does this mean? So now, instead of thinking of photon as a force carrier, which of course it will be, we are going to think of this as a gauge boson. So what is a gauge boson? For this, we first want to postulate that the standard model Lagrangian obeys certain symmetry. And this symmetry is what we are going to call as a gauge symmetry. So one of the gauge symmetries that we'll talk about here is the gauge symmetry of electromagnetism. That's where our photon will come into picture. So what is the gauge symmetry? Okay. So suppose psi, for simplicity, I just call it a wave function. Okay, but what I mean is a field, of course. But a wave function of a charged particle, okay, can be changed by this factor e to the power I times g times alpha. Now, if alpha were a constant, then this would simply mean that you change the phase of psi. And you know that if you know, since the phase of a wave function doesn't really matter, this is just a global change and Lagrangian will not change. So there is no big deal if alpha is a constant. Lagrangian that you saw on the earlier slide, if you want to remind me, both of these will get multiplied by e to the power I alpha times g, and those factors will cancel because there is psi, there is psi bar. So that is not a big deal. We are claiming that electromagnetism has even greater symmetry, which is in fact infinite times greater, which is to say that this alpha can be a function of x. And by x, I mean x, y, z, t. So this means that this value of alpha could be different at each and every space-time point, depending on how you like it. And even when I do that, the equation of motion of the electron will not change. Okay, so note that this is actually a very strong condition. I'm saying that wherever my alpha is, this should not change. Okay. If you try to apply this condition and go back to our old Lagrangian, you will find it does not work. Okay. The Lagrangian itself will change. So, for example, if I have e to the power I g times alpha here, this del mu will act on that, give you some extra terms. Okay. So clearly, then the Lagrangian will not stay the same, and all our postulated symmetry, the gauge symmetry, then it doesn't exist. Okay. But we want it to exist because it's going to give us something very useful. So what we do is, in addition to whatever we had earlier, we introduce a particle called the field A mu, which also transforms under this. If psi changes to this, A mu changes to this. A mu plus del mu times derivative of the same particle, of the same function, alpha of x. And in addition, at the same time, instead of taking a derivative that we had in the Lagrangian, we write del mu minus I g times A mu. And you could do this by yourself if you haven't done it yet 100 times already in your classes. Substitute this, do the gauge transformation, and you will find that indeed the Lagrangian ends up being the same as earlier, okay, except in the form of these new values of A mu and del mu. Okay. We are familiar with electrodynamics, and we have gauge theory. We remember that this scalar potential changes by del A by del T. Vector potential changes by some grad of alpha, P momentum goes to P minus E times A, and we do all our electromagnetism in our standard classical courses also. So it's exactly the analog of this. So what have we done so far? So we have found that if we postulate something A, which is now what we'll call as gauge boson, with this coupling constant, okay, then we can keep our Lagrangian invariant under this symmetry. Okay. So new Lagrangian, which includes this A, has this very special symmetry and a very strong symmetry, which says that whichever value of alpha you choose at every space and time, you will always have a symmetry in this Lagrangian. Okay. As physicists, we all love symmetries, because if you have symmetries, it means you need to give less information, right? So having a symmetry is always great. In electromagnetism, this A mu is what we call as a photon, and this G is what we call an electric charge. Okay, so it even connects very directly to our standard electromagnetism. Okay. So this was, in short, sort of one slide summary of what is a gauge symmetry and example of a simple gauge symmetry of U1 electromagnetism. So if you put this A particle in, what does the Lagrangian become? So this is the earlier Dirac term, psi bar I gamma mu del mu psi. Okay. Plus, because I changed the value of my del mu to del mu minus I G times A mu, I get this term, okay, which is E psi bar gamma mu psi times A mu. But now, since I also have this term A mu, I have to write its own kinetic energy part, and that part, as you would have seen in your classical electrodynamics, is written as F mu nu, where F mu nu is del mu A nu minus del mu A nu. Right? You have, I guess many of you have seen this earlier. Okay, good. Yeah, so here is the definition of this. So what do we normally do? We try to write down the corresponding Euler-Lagrange equations. Okay. We do Euler-Lagrange equations with A nu, and actually what we end up getting are Maxwell's equations. Okay, so Maxwell's equations are simply obtained by taking Euler-Lagrange equations with respect to A mu. We can also get equation for electron by doing a derivative with psi. Notice what has happened. This term was the term that tells you how a free electron behaves. This is a term which tells you how a photon behaves if there is no electron. And this term, which has psi bar, psi, and A mu, tells you that there is some interaction, okay, between psi bar, psi, and A mu. This interaction has the strength given by whatever coefficients are here, which is E times gamma mu. And that indeed is the strength of electromagnetic coupling. Okay. So when you will draw Feynman diagrams, in which you want to say that an electron and a photon combine to give a second electron, the coupling strength of this vertex, okay, forget about factors of I and all, they come for convenience. The coupling strength of this is E times gamma mu. Similarly, if you want to say that an electron came in, emitted a photon, and then gave another electron, the coupling strength of this vertex is going to be E times gamma mu. So when we proposed a symmetry, okay, not only did we say that there is interaction between electron and photon, firstly, before that, we proposed a symmetry. It told us firstly that there must exist a photon. Okay, so the existence of photon was in fact implied, okay, by the fact that there was a symmetry. Second, it told us that there is an interaction between this photon and this electron because there is a psi bar psi atom. And thirdly, it also told us that the strength of this term, the strength of this vertex, is E times gamma mu. E was the coupling of Lick constant. Okay. So just saying that there was a U1 gauge symmetry already told us a lot. In fact, it told us everything about equations of electrodynamics. Okay. So saying that it's a gauge symmetry is a very, very powerful statement. And when I make that statement, I am actually adding a lot of information to what we know. Okay. So this is the principle about gauge symmetry, and I'm spending time on this because standard model has not only U1 but also has slightly more involved symmetries, which we are going to come to very soon. Okay. So what do we do for gauge symmetry? We find out a local transformation. By local, I mean that the value of alpha of x can depend on wherever you are. This can change the wave function of a particle or a field, but it does not change the equation of motion. So the particle ends up behaving the same. Okay. So observables are not affected by this transformation, and hence we call this symmetry as a gauge symmetry. We call this as a symmetry. So as I mentioned, this forces the existence of a gauge boson, and all interactions are fully fixed. Okay. Turns out, okay, it's a coincidence in some sense that our world, at least the electromagnetic strong and weak forces, seem to obey such gauge symmetries, and that's what makes our life much easier. Okay. So let's try to understand a similar kind of gauge symmetry structure for strong interactions. Okay. So what symmetry do we know in strong interactions? Okay. So we saw that all the quarks come in 3 colors, okay, and there are interactions between them. Interactions are carried by gluons, and the interactions is what we call the strong force. There's something more than that. So for example, look at this interaction. This is where a red quark goes to a blue quark, and that means that there was a gluon which was red times blue bar, which allowed this to happen. Similarly, a green quark here has gone to a red quark, and there's a green red bar gluon which allowed this to happen. So all the possible combinations here actually exist, but that's not enough. The coupling constants at all these vertices are identical. Okay. They do not depend on what color quark is coming in and what color quark is going out. That's the reason for us to postulate that there must be some kind of symmetry in strong interactions. So therefore, just like we expressed electron as a gauge boson of electromagnetism, now we are going to think of writing a gluon as a gauge boson of strong interactions. So how do we do that? So for electrons, remember, we had to multiply the wave function by e to the power I g times alpha of x. Here, now we have 3 particles: red quark, blue quark, and green quark. All of them can mix amongst each other by using this gluon. Okay. And therefore, what my wave function should change by is not just a simple factor of e to the power I alpha x, but any unitary matrix. E to the power I g alpha x is a unitary number with magnitude 1, because it was just one dimensional. That was U1. Now I'm going to SU3, so I have 3 particles, and therefore I will need a 3 by 3 matrix to rotate that into another wave function. And my claim is that if I do this, my Lagrangian should stay the same. Okay. So earlier we would have given up, but now we know this great technique of adding gauge bosons, and things just seem to work. Okay. So what do we do for this slightly complicated beast? You can still do this if you have particles, which are now called as G mu. Okay. Now what do I do? Firstly, this G mu under this gauge transformation transform in this way. Now this way looks a reasonably complicated way, but it's not really complicated. Okay, it only involves this transformation U and some of its derivatives. You might have seen its infinitesimal version, in which case actually this becomes a simpler equation, but I simply wrote down the most general one for to show you that this U appears here explicitly. Our derivative again changes very similarly. It changes by this extra term I times G3, which is this coupling constant, times G. And I will not show explicitly, but it just, you can work out. It just turns out that Lagrangian, if you write with these 2 transformations, will be invariant under this U of x. Okay. So any transformation of this kind, transformed by a 3 by 3 matrix, will still keep a Lagrangian invariant. Okay. This is what we call as the SU3 gauge symmetry. Okay. So this symmetry, these G mu's, is not just one particle, but a set of 8 different particles. And the reason for that is that this is the 3 by 3 unitary matrix. Okay. And this you can write in terms of 8 generators of SU3. SU3 happens to have 8 generators, Pauli matrix, not Pauli, Gell-Mann matrices, right, that you might have heard about. And these 8 generators correspond to 8 independent values of G mu A. So A can go from 1 to 8. So 8 components. These 8 components are our 8 SU3 gauge bosons, which are what we call as our 8 gluons. Okay. So now this tells you, in analogy with our electromagnetism, we had 1 photon. Here we have 8 gluons. And the reason for that is that the symmetry of quantum chromodynamics, the theory of strong interactions, is much more richer than the electromagnetism that we have. Okay, that's the reason to make the symmetry valid, we need 8 gluons. Okay, so GAs are the 8 gluons, and G3 here is a strong coupling constant. Okay, so again, what has happened is, because I made a statement saying QCD has SU3 gauge symmetry, we predicted that there will be 8 gauge bosons, which are gluons. So we predict the existence of gluons. And on top of that, we predicted exactly what the coupling of the gluons with standard model particles is going to be. Okay. So essentially, we know everything about quantum chromodynamics. Okay. It may be difficult to calculate, but we know where to start from. Okay. So just like we had a photon as a force carrier propagating between 2 electrons for electromagnetism, now we have, let's say, this red quark and this I don't know, maybe green quark traveling. They can exchange a strong force by the exchange of a red green bar kind of gluon, and as you see that their colors will change. So we have these 8 gluons, all these RG bar, GR bar, BR bar, and so on, all the combinations that you can make, which are called color gluons. The 2 gluons which are called as white gluons, but they are still proper gluons. This is just the nice basis. You can form 9 combinations out of RGB and R bar, G bar, B bar. One of them is a neutral particle. This has all colors in the same strength. So clearly it will not take part in interactions. Okay, so therefore not 9, but exactly 8 gluons. Okay, so then to us, strong interactions look almost the same as what electromagnetism is. Okay, just with a larger gauge group. But that would be speaking too soon, because we know that they are actually different. But this is the proof that it actually exists. We saw it yesterday. This was the 3-jet event at the Tasso experiment, which showed you that gluons actually exist. Now, these gluons are different from photons. They have many different properties. And a major one is that they actually, although they are massless, they contribute to most of the proton mass due to their momentum. So in proton, we have up and down quarks. Masses of up and down quarks are of the order of about 10 MeVs. Mass of the proton is about 900 MeV. Okay. So the whole difference between these, about 20-30 MeV to 900 MeV, actually comes from the momentum of gluons, and also of course partly of momentum of the quarks. Okay, so the exchange of gluons among quarks inside a proton actually binds them together with a property called as confinement. And the confinement means that the gluons, although they are massless, do not fly away to infinity, but keep on confined together inside a nucleus. For this to happen, we do not have to postulate anything new or any new concept. The fact that a group is SU3 already tells us that automatically, and that's also another major thing that never fails to surprise me. The difference between electrons and gluons and photons, okay, comes from the following. So remember, as you take away 2 electrons far away, the force between them will decrease, 1 by r square. If you look at interactions of photons, it turns out that that doesn't happen actually. The force between them, between the quarks, the strong force actually will increase when you pull them apart. And in fact, therefore, if you try to pull apart two quarks, they will actually break up into two mesons. So take a meson, try to separate the quarks, and you will get two mesons. This is exactly the reason why you get jets in your detector. Okay? That's the reason that you end up getting the jets. So the main difference between the theory of quantum electrodynamics and quantum chromodynamics is that if you go from low energy to high energy in QED, okay, using quantum corrections, which we will not go into, but I'll just give you the result. The value of coupling constant alpha actually increases if you go to high energy. Whereas in the case of QCD, the coupling constant actually decreases. And this tells you that if your energy is very high, the strong coupling constant actually will become very, very small. Okay, so small that it can become perturbative, you can neglect it. This happens to be one of the major reasons why it's reasonably easy to calculate in LHC than it would have been at colliders with lower energies. Because at high energies, the strong coupling constant is small, and therefore one can do perturbative calculations at high energy. This was just a remark. Okay? So this is the main reason of difference between QED and QCD. At low energies, the value of alpha is quite large, becomes of the order of 1. So that's when you cannot use perturbation theory and quarks get confined. At very large energies, quarks are asymptotically free, which means that the interaction between them decreases quite a bit. Okay? So that is one major difference. And that actually gives you, well, discovery of that gave these three guys their Nobel. This also tells you that something more should happen with strong interaction. Okay? So firstly, just by the nature of SU3, the force carrying particles which are gluons are themselves have color, right? This has GR bar, this has BG bar, and so on. In electromagnetism, for example, photons don't have charge. Okay? So there is no photon-photon interaction. Okay? In the case of quantum chromodynamics, gluons themselves have color, and therefore there is a gluon-gluon interaction. Okay? So in fact, it turns out that in addition to a gluon interacting with two quarks, you can also have three gluons interacting with each other. Not only that, we can also have four gluons interacting with each other. And the fact that they can do this, you will obtain simply by doing the substitution that I mentioned earlier. You substitute in your Lagrangian, you add this extra component of a gluon, and you will find that you will indeed have vertices which give you gluon, gluon, gluon. So G, G, G kind of vertex, capital G. And you will also get vertices of the kind G, 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 which means gluon, 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 gluon. It will tell you that indeed four gluons can also interact. So interactions of electromagnetism and strong interactions are even at the basis point very, very different. Because of this, as you know, earlier we had mesons and baryons, which had mesons had quark and anti-quark, baryons had three quarks, such that the colors of the quarks here also cancelled. But in addition, it is possible to get an object called as blue ball, which has no quarks at all, but it consists of only gluons. Okay? There are, of course, there are candidates for glue balls which have been found, but it is actually quite difficult to conclusively show that a particle seen in the experiment actually is a glue ball. Okay? The fact that some of the candidates are glue balls, that information comes to us also partly from our calculations of lattice-gauge theory. Okay, but this is one major difference. You will never find a photon ball, right? So it's photons don't interact with each other, but gluons can interact with each other, and they can actually bind themselves together. Okay, so that is one more prediction that standard model tells us. Okay, fine so far. Any questions on this? Yeah.
So why this -1/4?
So this is a standardized normalization. Okay, a standardized normalization. We want to normalize things such that we write that in the QFT language, but we also want it to come down to our usual limit of in the usual limit, it should correspond to the kinetic energy, half mv square. So this normalization is formed by taking that into account. That's the reason for this 1/4.
So 1/4 is because of the whole terms are being averaged out. All the terms. 1/4 is because of all the terms are averaged out.
Yeah. So you have del mu a nu. Remember, okay. So not the exact answer, but answer that may sometimes it gives you a hint is, see, remember f mu nu has two terms. Del a, del a minus del a, right? So when you square, you are going to get 4 terms, and 1/4 will normalize that. Okay. So that's an answer that, okay, it's an answer that satisfies people, but it's not the right answer. Okay. So, but yeah, you could take that as a motivation for 1/4. Okay, but the right answer lies slightly deeper. So let me talk about that.
I just think that you are not coming in. Just say you are about tetraquark, pentaquark also.
Okay, so since on the special request of the organizer, let me also tell you that these are not the only bound state of quarks that we have found. We now have found tetraquarks, which means particles which have 4 quarks in them, which are bound states. Particles which have 5 quarks in them. These have been found at Bell 2, definitely. LHCb also. Tetraquarks. Tetraquarks found it.
That is confirmation is instead of Bell 2, it was there, but it was not finally confirmed.
Okay.
LHCb is much more fun.
Okay, so sorry about that. Yeah. So at LHCb, we have now found tetraquarks and pentaquarks. So these states, for example, have energies which are less than the energies of 2 mesons that could be forming this state. Okay. Many of them have at least one heavy quark in them, with either B quark or a C quark. So either 2 heavy quarks in them, normally 2 B quarks or 2 C quarks. Anything more? Please ask Govinda.
You mentioned about the chirality part from neutrinos. So how do you measure the neutrino chirality?
No. Yeah, so good question. You do not measure neutrino chirality. Okay. In an experiment, if you just want to measure the spin of the particle, what you end up measuring is actually helicity. Chirality is a good theoretical construct to be able to calculate things. Okay. To say something is particles are left chiral or right chiral, to describe their interactions.
So when you say that right chiral neutrino is not observed, is actually helicity you are telling, means you have not measured right-handed neutrinos.
No. So the statement is to both ways. Okay. A, we have not seen right-handed as in right helical neutrinos, but that is not because they don't exist. That is because we haven't done an experiment which is sensitive enough to do that, because we know that the fraction of right chiral neutrinos is going to be very, very small. It depends on mass over energy. So that number is very hard to obtain in the experiment. Okay. But we are sure that right helical neutrinos exist, because neutrinos have mass. Anytime a particle has mass, you can always move faster than that and make a left-handed into right-handed particle. Okay. Chirality is a relativistic notation, relativistic covariant quantity, in the sense if a particle is left chiral, by applying Lorentz transformations, you cannot make it right chiral. Okay. And therefore, we know that left chiral neutrinos exist. Okay. We have not seen right chiral neutrinos, and we do not even know that they exist. There has been no evidence. Yeah.
So I have one small question. In the QED coupling strength plot,
there was a point marked with alpha is equal to 1/128 at, I guess, MZ energy state. Is that a theoretical prediction or it is measured?
Both. It also has measurement. I will show the measurement near the end of today's class. I have a experimental plot there. Yeah. It's just one there. Yeah.
But okay. So you said quark confinement. So gluon don't fly away to infinity. So here, yeah. So they just bind the quarks, and this is explained by SU3 gas symmetry. Can you explain?
Beyond that, I cannot explain because beyond that,
I mean, how the
confinement-
SU3 is explaining quarks don't fly away to infinity.
How, sorry?
How the SU3 gauge symmetry is explaining quarks
So-
don't fly away.
Yeah. So I'll tell you the way to do this. Okay. The way to do this is calculate quantum corrections, okay, and find how the coupling constant of SU3 runs. Okay. How the coupling constant changes. And that will give you the kind of plot that I showed earlier. It should tell you that the coupling constant, if you go to low energies, actually becomes very high. And when the coupling constant is high, things stick together. Okay. So you calculate what's called as the QCD beta function. Okay. That's the keyword that you go and look for, and you will find how to do it.
Okay, it's just to mention that we have already found at LCB the pentaquarks. Yeah,
Yes, indeed. Yes.
yeah. And my question is about neutrinos of Majorana. If
Uh-huh.
you can tell me something about that, because I cannot truly understand how that works. And
Okay.
because you mentioned in the beginning the neutrinos, and I was thinking about that. Thank you.
Okay. So let me just mention your answer shortly, and we can discuss about it later because that's going to take us into a large domain. So, in fact, maybe I'll talk about it later because I'm going to talk about how quarks get mass, and that time I'll mention why neutrinos do not get mass like that, and then we'll talk about Majorana neutrinos. We'll come to that. Yeah. Okay. Now that we understood strong interactions, weak interactions follow exactly the similar path, so we can actually go reasonably fast. Okay. Firstly, just to remind people, the weak interactions have strong effects. Beta decay, they appear in all the cosmic ray showers, and indeed, the shining of the sun, they are quite important. So they are not just very weak interactions. Okay. Effectively, what one observes is this, because the interactions happen at a very small scale. This is the effective Fermi vortex, which is given the strength of GF, for example, for muon decay. But actually, we know it happens by exchange of W or Z particles. And the symmetry that we observe from experiments, just like in the case of strong interactions, we said that all those couplings were exactly the same, GS. The couplings that we find in the nuclear beta decay, in muon decay, in decays of pions, in decays of kaons, are all exactly the same, related by the mixing angle called Cabibbo angle, but that will come to tomorrow. But the fact that these are governed by exactly the same coupling constant motivates us to say that there is some such symmetry. And once we know the symmetry, now that we have tested the blood with SU3, we can go to SU2 in exactly the same way. Okay? So we know there has to be a pair of fermions, psi1 and psi2. There should be a 2x2 transformation, unitary one, which can take to something else without changing the equation of motion. Okay? And turns out that it can happen if there are particles W mu such that they undergo these particular transformations. If you see, they look exactly the same as what we did for G. Okay? For SU2, the difference is that we only need 3 independent W mu A's here because it's a 2x2 unitary matrix. So you can have generators of SU3, of SU2, which are only 3. These are the 3 Pauli matrices, sigma 1, sigma 2, sigma 3, which you will be familiar with. Okay? And that's it. So now these 3 WAs, W1, W2, W3 are gauge bosons, and G2 is the weak coupling constant. Okay. And then we get W's, and there are 3 coupling constant W's, and there's Z. Z is not the same as W3, but we will come to that very, very soon. And we know that they exist. This is the same figure that I showed you yesterday. Okay. So overall, now we know the standard model has a gauge theory structure. The gauge theory is SU3 color, type SU2L. SU2L here is because only the left chiral fermions interact with W. There is U1Y, the hypercharge. Quarks are charged under SU3 color, so they interact with gluons. Leptons are not charged under SU3 color, so they don't interact with gluons. Left-handed particles are charged under SU2L, so they interact with W. Right-handed, so right chiral particles are not charged under SU2L, so they don't interact with W. Now this SU2 cross U1 is spontaneously broken by Higgs boson, giving rise to electromagnetism, which you call as U1Q. So in some sense, even electromagnetism is a result of Higgs. and we will see it in the next 10 minutes, how that happens. Okay. So this all allows us to write down the standard model on just one slide, all interactions in just 5 lines. Okay. Just have to understand what these terms mean. So first line is this line of kinetic energy terms of the W bosons, the weak interaction terms. This is the hypercharge boson B, and these are 8 gluons. Okay. So these objects, which are called W mu nus, are given by this. Okay. In the case of a photon, in the case of this U1, this W cross B is 0, and therefore you only get a familiar terms of del mu B nu minus del mu. Okay. So this first term tells us about the kinetic energy of all the gauge bosons that we have, and this term will exist even if there were no fermions in the world. Okay. Second term has this thing called L. Oops. Now this L is a pair. It can be either U or D, but left-handed, or neutrino and electron, again left-handed. That's why they are called L. Okay. So remember that because these satisfy the gauge symmetries, we had to add terms like this, no, minus G by 2 W dot tau. So you have to change del mu by this factor because there is weak interaction. Okay. For interaction with U1, we have to change del mu by del mu minus G prime by 2 times B mu Y. Okay. So all that happens is, instead of del mu, you get this term, which tells you that these L's are charged under hypercharge, which is B, and are charged under weak interaction. U and D also are charged under strong interactions. Okay, but not to worry. All that you have to do is add another term here inside bracket, which is minus G3 by 2 G dot lambda, the Gilman matrix. Okay. So this takes care of all the left chiral fermions. Similarly, the next line takes care of all the right chiral fermions. So this R, for example, can be a right-handed up quark, a right-handed down quark, or right-handed electron. Okay, and of course, if you have quarks, then you have to add this term because quarks are charged under SU3. This term will tell you about Higgs. This is the standard model Higgs that we have. This is also charged under hypercharge and weak interactions. And therefore, you get a term like this. Higgs does not have a color charge, so it will not have a G term. This is Higgs potential. And the remaining 2 terms rather, plus Hermitian conjugate, these are terms called Yukawa terms, which tell you what are the interactions of Higgs with one from L and one from R. Okay, so that is the term which will end up giving you masses for Higgs. Okay, so once you understand what a gauge theory is, and once you have this slide in front of you, this is like Maxwell's equation T-shirt, no? You can essentially write down all the interactions of standard model, and they will be at your fingertips. Yeah.
So this is not only the ULP, this is all of the family.
Yeah, sorry, yeah. So I written examples of the first family, but of course all families will be big. Yeah, thanks. Okay, so that's what we have. The model with all these particles, we can write down the SU2 and U1 charges. Higgs, for example, in particular, has SU2 doublet, but it has hypercharge equal to 1. That is going to come in handy in the next 10 minutes of my lecture. So as you see, we are not very familiar with the hypercharges of particles. There are numbers like 1/3 and minus 2/3 and 1 and 2 and so on. But this is very important to remember that the Higgs that is a part of standard model has hypercharge equal to 1. Okay, we will come to it very soon. Remember that none of the particles has a mass yet. Okay, we did not write any mass term. In fact, we are not allowed to write any mass term because if you write a mass term, then the gauge symmetry will not be valid. Okay, and that's the reason that it is not possible for any fermion to have mass and any boson to have mass with this kind of Lagrangian. Okay. As soon as we put in mass term, gauge symmetry is broken and all the nice properties we have of the standard model will simply collapse. Okay, so that is a big problem. The solution of this big problem is obtained by the mechanism of electroweak symmetric breaking. Okay, and that is the importance of Higgs. So electroweak symmetric breaking, what happens? So I will not go through all the calculations, but I will indicate to you what is being done. The Higgs that we have has a potential that looks like this. Okay, this Higgs is are two complex numbers, so it's written like this. But the mu square has a negative value, which tells us that actually the minimum of this potential is not at phi is equal to 0, but at some other place, which is called as vacuum expression value of the Higgs. Okay, so the minimum is on the surface of a 3-sphere, which actually satisfies this criteria. Okay, spontaneous symmetry breaking means that you break this symmetry out on this sphere and choose one point on the sphere. What we normally do is we choose that point which has phi 3 equal to V, and all the other three are 0. So which means it only means there's a V here and everything else is 0. Okay, which is like saying that my phi has a form which is 0 and V plus H of X. This H of X will be the Higgs field that we'll actually end up observing. This will be the vacuum expectation value. Now note that this is vacuum. In vacuum, you have this particle which exists. Well, not particle, this is just a vacuum. This has T3 or isospin component. So T3 is not conserved because for this T3 is minus half. Remember, Higgs had Y equal to 1, which means the vacuum has Y is equal to 1, which means vacuum will not conserve Y. Hypercharge will not be conserved in vacuum. So both T3 and Y will not be conserved. However, if you calculate T3 plus Y by 2, that will be conserved. And because the sum of these is 0 for this quantity, and this quantity happens to be exactly the same as electric charge. And that is the reason that when electroweak symmetry is broken by Higgs mechanism, electric charge is still conserved. Okay, and that's the beauty of this mechanism, which I wanted to point out. If you look at the Lagrangian and now try to rewrite the Lagrangian in terms of this phi and H of X, you will actually find that don't go to algebra, you will find that there are terms that look like something square times W1 square plus something square times W2 square, and these two terms now give masses to W plus and W minus. Okay. You also get a term that looks slightly complicated, but it will depend on a combination of W3 and B, the boson of hypercharge. If you take this quantity and you diagonalize this, then you end up again getting two eigenstates which have masses. One has a mass equal to 0 and second has mass which is given by this. The zero mass object ends up being what we call as photon now, which is our gauge boson of electromagnetism. And the second remaining part, which has a mass of G square plus G prime square, is Z. Okay. So now what we have, and of course, angle of rotation is what is called as Weinberg angle. So now we have mass of W connected to vacuum expression value of Higgs times the coupling constant, mass of Z connected to again wave of the Higgs times coupling constant. Rho is the ratio of these two quantities, which is always 1. And the measurement of rho parameter is again a very major test of Higgs mechanism. Okay. So these are very strong predictions of Higgs mechanism of the standard model. In addition, remember that we had interaction terms with fermions, L bar, phi, right? Okay. Now, when this phi gets its wave, it turns out that these terms exactly end up giving masses to up quark, down quark, and electron. And again, these masses are proportional to the vacuum expression value of the Higgs multiplied by its coupling constant. Okay, this is the time I wanted to answer my neutrino mass answer, but I will finish my lecture and then answer this question. Then there is so very quickly, I'll just show you 3 nice experimental tests that have tested this nice edifice, which is reasonably complex, but gives a large amount of predictions, some of which even unexpected. So this is just a sample of 3 things. Okay, actually there will be thousands of them. Every experiment I do is actually test for the standard model. So one is the running of alpha strong and alpha electromagnetic. Note that this is alpha S and this is 1 over alpha electromagnetism. Okay, so alpha S decreases at large energies, alpha electromagnetic increases. Okay, and this is the measurement that somebody perhaps said happens at, so this is, if you go all the way to 0, you will reach 137. That's why we say alpha is 1 upon 137. But that just a coincidence, only happens at q square is 0, as it actually alpha increases. And at this point, it has a value of 1 upon 126, which is a measured quantity. Okay, this is a left measurement. This is actually L3 plot, so it must be L3 measurement. Second important thing, which you have perhaps also seen, I think you showed it yesterday, this plot. No, you did not. Okay. This is a plot in which we plot particle masses versus their coupling with Higgs. So remember, we had relations of the masses of fermions with Higgs and also those of masses of W and Z bosons with Higgs. And you see that all of these right now seem to be very nicely satisfied to a very large precision. Here you see the precision almost about 10% in everything else. Muon is slightly lighter, so it's about 30% or so. You will need more data for this. Okay. And the third thing, which is not exactly standard model, but it's important for the existence of standard model, is the fact that the Higgs vacuum has to be stable. We said that Higgs doesn't have vacuum at 0, but somewhere else, and that's where we live. But we should also be sure that we'll keep on living here forever, because the potential can have a complex form, which will make this metastable. Quantum corrections actually do this, change the form of Higgs potential and can make it metastable. And the stability condition actually depends on the exact mass of Higgs and the mass of top quark. And that's the reason this is region of instability. This is region of metastability, which means that we will perhaps go into some other vacuum at very, very long time scales. But this is also region of stability. So to figure out where we are, we need to find Higgs mass and top quark mass to very high precision. Okay, so measurement of these two is very important, and the measurement of all these masses, especially fermion couplings to Higgs, decays of Higgs to fermions, is very important if we want to see that standard model is actually correct. Okay. So I will stop here. That's a good time to stop. I will take questions and maybe answer some questions that I have not addressed during this talk.
Questions?
So I will answer the question of Majorana neutrino that came, and I promised him that I will answer. Okay, so as we saw, to give masses to fermions, we need a left-handed fermion, a right-handed fermion, and Higgs. Right? Now, as we said, we do not have a right-handed neutrino. We don't know if it exists or not. Okay, in principle, it can exist, and maybe that is maybe the mechanism to give mass to neutrinos. But neutrinos, by their nature, do not need a right-handed neutrino to give their masses. Okay, it is possible to give masses to neutrinos by simply having left-handed neutrinos. That mechanism is called as the mechanism of Majorana masses. It can be done if neutrinos are Majorana particles, which means that it happens to be its own antiparticle. It is allowed by the standard model so far. Okay, standard model has this symmetry called lepton number conservation, which is not a fundamental symmetry. I didn't mention it today, right? Standard model can, in principle, violate lepton number, and if that happens, in that case, neutrinos can get a mass even if they are only left-handed. Okay, and there is a whole field of giving masses to neutrinos, various mechanisms using this concept of Majorana neutrinos. So we can talk about that later.
Any further questions?
So, does chiral restoration and deconfinement occurs at the same time or at a different time?
Sorry, can you repeat that?
Chiral restoration and deconfinement.
Okay, chiral restoration, I'm not exactly sure what you mean by that. Maybe I haven't.
Chiral breaking, chiral symmetry breaking and deconfinement. In the case
Chiral symmetry making a deconfinement. Around the same energies, but not the same. Reasons are different. No, so chiral symmetry breaking has to do with fermions. Confinement, deconfinement has to do more with gauge bosons. Okay. Again, I am not an expert in QCD, so somebody else can give you a better answer than this, but this is what I understand.
Okay, thank you very much, Professor, for your nice presentation. I have a simple question related to mass Yuka coupling.
Need to go back.
Second last slide. maybe. Second last.
Yeah.
No, that is plot. Plot.
Oh, the
related
plot.
to mass Yuka
Plot. Okay.
coupling. Okay.
Yeah.
Oh, what physics behind that 30% error bar? In the case of gluon, right? What is the physics behind this? That error bar?
Oh, this error bar.
Yeah.
No, so what is done is the following. Okay. So of course, particle masses are measured and they are put on the x-axis. The y-axis, what is plotted is the decay of Higgs to a pair of fermions. So for example, you can see Higgs going to BB bar. Okay. If you try to determine the branching fraction of Higgs to BB bar, it will tell you about the coupling of Higgs to BB bar. Okay. Remember, this measurement is completely independent of the BB bar mass. Okay. I just have Higgs produced goes to BB bar, and that will tell me what is the coupling of Higgs to BB bar. And that coupling is plotted here on the y-axis. Okay. So this is KF. So this is, so that, let me see. Yeah, okay. So that coupling is plotted.
My question is, at low energy, why there is 30%?
No, it's not low energy. This is particle mass. So, for example, muon has a mass of 100 MeV.
Yeah.
So it's plotted at 100 MeV. Okay. So let's say do the following. You take a particle, muon. Mass is 100 MeV, so x coordinate is 100 MeV. Then you find out the decay rate of Higgs going to mu plus mu minus. That rate you plot on the y-axis. Now that rate will be proportional to the square of the coupling. Okay, so you take the square root and plot it on the y-axis. Then you take a fermion like tau. Okay, and you find the mass of tau 1.77 GeV. Against that, you plot the decay rate of Higgs going to tau bar. You take B meson, which has mass of about 4 GeV. Against 4 GeV, you plot the decay rate of Higgs going to BB bar. Okay, now arbitrarily speaking, there is no relation between the mass of a particle and its coupling, right? They're independent. Okay, but the fact that muon, tau, B, and T, they all lie along the same line, okay, gives us confidence that our mechanism for mass production is true, that the mass is given to all the fermions by coupling with Higgs, because these four lie on the same line.
Thank
Okay.
you.
Similarly, W mass was mW square was G square half G square V square. Okay, so again, mass of W is proportional to the same quantity, which is the wave of the Higgs. Okay, and therefore it's important that even they lie on the same line. So that is a very strong measurement of our standard model.
So I have a question. This, how do we measure the bare quark masses experimentally?
Huh?
Means how do we measure this bare quark masses experimentally?
So the answer is we do not measure bare quark masses experimentally. So measuring quark masses, determining quark masses from experimental data is a whole thing on its own. Okay, again, I am not an expert in this. You should ask. There are people in TIFR who actually will answer to that in a much better way. But it definitely, one thing I can tell you confidently, that you do not measure bare quark masses directly at experiments. You have to process them somehow and end up getting the bare quark masses. If there is anybody here in this room, please feel free to answer the question. You are answering the question, or you are still in stop?
I think we have enough time. I think we stop at the last question.
Regarding the charm quark there in the plot, I mean, it's, I mean, is it due to the like difficulty in measuring the mass of bare quarks that the charm is not there on the line?
not mass. Measuring charm quark mass has been known for many years. That's not a problem. As you see, it is the coupling with Higgs that has large errors. We have not yet observed conclusively decays of Higgs to charm. See, Higgs to muon, although muons are lighter. So remember, when you go to lighter and lighter fermions, coupling decreases, right? And cross section becomes, the decay rate becomes square of coupling. So as you go from here to here, it will become harder and harder to produce these particles. So therefore, this way things are harder. Now, muon happens to be easier to measure because CMS was built to see muons. Right? Atlas sees muons very easily. Therefore, even though decays to muons are smaller in number, they are more easily observed. And that's why we have a muon measurement. But charm quark, the cross section is small and is difficult to identify from the mesh that you get at LHC. And therefore, there is no measurement till now of Higgs going to CC bar. That's the reason you get this larger output.
I think we have to stop this discussion. Further discussions only up at a tea break. And
Okay,
thank you,
fine,
Amol.
I'm around.